So, welcome back. I hope you all had a great weekend. So, did you receive your grades? Did you check on Teams?
Yes, sir.
Yes? And I hope you guys don't have any complaint, as I have already given the reasons, not explicitly, but from my answers, you have known where I have deducted your mark. Okay, so if I haven't commented on any question, so then you know that you have got full marks in that particular question. Okay, fine. So, and again, I have decided that for the time being, I am going to hold a series of quizzes for you. So probably the next quiz is going to be somewhere in the middle of October, where we had a scheduled class on Saturday. So on that particular Saturday, I'm going to have your quiz too. And definitely I'm going to announce it beforehand. Okay, fine. So let me come back to what we learned in our last class. So we were talking about this Wronskian, firstly, of two functions as solutions, and then we have given you the Wronskian for the solutions which are linearly independent for a nth order differential equation. Okay, and over there, it was found out that the Wronskian can be put in this form, e to the power minus px dx. Okay, if your first order differential px dx, if your a second order differential equation, it is put in this form. Okay, so this is the Wronskian. Okay, and if I am considering an nth order differential equation like Pn minus 1x, yn minus 1, say eventually P1y prime plus P0y equal to 0. So then this term Px is simply replaced by Pn minus 1. So we have already done this in our last class. Now, many of you told that how to find out the constant C. Like I can simply write it as like Wronskian at the point x0, where your initial condition is specified, and then I can simply write it as. But the question is, in order to find out this one, in order to find out the value of the constant in terms of the Wronskian itself, you'd have to know the Wronskian explicitly, isn't it? Right? Are you getting my point?
Yes, sir.
Okay. Yes, so it is simply like the epic Ramayana. It was written before Lord Rama was born. So it is exactly like this sequence, isn't it? Fine. So now, and again, I have given you a way of finding that constant. What was that? And it was, I told you to work it out, okay? And I told you that you proved that this Vx is a constant function. But probably I forgot to tell you how to go about it. So what you have to do, you have to simply show that your v prime x, this is equal to 0, and then from here your Vx will come out to be a constant. Okay, so then if this is a constant, so then for any value of x it is going to work. And again, just a minute, I can write it like this, but here if I write this function as x0 to x, then once you prove that v prime x is equal to 0, so that means v of x is constant. So then you simply plug in, here instead of x you plug in x0. So this is going to give you e to the power 0, that is equal to 1. And from here you can easily find out the constant. Okay, is it okay? So from there you can do it. So that is all about the Wronskian. So now what I'm going to do, I'm going to tell you how the use of Wronskian can help you in understanding the behavior of the solution, But I think that is going to be a long shot for today. I don't know whether I'll be able to reach that or not, because before that, I'd like to cover something more on Wronskian, and then some solution procedures for your second order linear differential equation. Okay, fine. Now, okay, let me ask you one question here. Okay, suppose I am considering a second order, homogeneous ODE. Okay, fine. And suppose y1 and y2 are linearly independent solutions of this equation. So then, can you tell me why, y1 and y2, they cannot vanish at a common point? Yes?
Yes, sir.
Yes?
If they vanish at a common point, their Wronskian will be 0.
Wronskian will be 0. Yes. See, if they vanish at a common point, the Wronskian is going to be 0 at that particular point. Say, let me say it as x naught. Okay, that is the first thing. The second thing is that again the same thing is going to occur if they have maximum or minimum, right, at a common point. So in that case, what is going to happen? Either your y1 prime or sorry, not either. So both of them are going to be 0, right? And again, in that case, from the definition of Wronskian, the Wronskian of the function, Wronskian of those two functions at the point x naught, it is going to vanish. Is it okay? Fine.
Yes, sir.
Right. So, but the thing is that if I ask you this in exam, like a quiz, so if you simply tell me that okay, if because the Wronskian vanishes at that particular point x naught, right? They cannot be linearly independent. Y1 and y2 cannot be linearly independent. But I'm not going to award full points for that. Can you tell me why?
We need to prove Wronskian is either identically equal to 0 or not equal to 0.
Yes, so that's it. Yeah, I understand. I understand what you were saying. So basically, you have to tell me that the Wronskian is going to vanish throughout the whole interval on which you are going to define the solution of the differential equation, right? And we have already seen that the Wronskian either vanishes, right? It is either 0 or either non-zero throughout the whole interval. So that means if it is non-zero at one point in the interval, so it is going to be non-zero throughout the whole interval. So that you have to mention. Okay, fine. So, and again, see, these two facts we are going to require later on when we are going to study the qualitative behavior of solutions of ODE. So now, this is done. So, okay. So now, let me just quickly do, two things. I don't know how much time is going to consume, So what I'm going to do, say, suppose I am giving a second order linear differential equation given by this. Of course, I am considering a homogeneous equation, right? So let me try to find out, let me try to do one thing. Say, suppose I know that y1 is a known solution of this equation. Y1 is a known solution of this equation. So then, obviously, for this equation being a second order ODE, so I can find if at all it exists, I should be able to find a fundamental set of solution consisting of two elements, isn't it? So whether I can find the second solution in terms of a known solution. Okay? And second solution, of course, I am seeking a fundamental set. So that means I am seeking another solution y2 in such a way that y1 and y2 is going to constitute a fundamental set of solution. Okay, fine. So one way I can think about is, okay, let me just simply plug in y2 equal to some constant into cy1, right? cy1. So is it going to work?
No, sir, they are linearly dependent.
Yes, then they will be linearly dependent. Okay, so I cannot state this one. Okay, so that is where the idea of considering, say, this parameter c as a function of x. Okay, so for that, let me assume that this c, like here, I'm not going to write this is equal to. So instead of that, let me write that y2 is something like vy1, where v is a function of x. Okay, so then, like, if this is the solution, so then what is going to happen? Your y2 prime, so this is going to be equal to your v y1 prime plus v prime y1, right? And then your y2 double prime, it is going to be v y1 double prime. I would like to write it in this way. I'm going to tell you. Say, okay. Say, like, say here again, you are going to have v prime y1 prime, right? From this term also, you are going to get v prime y1 prime, isn't it? Fine. If you use the product rule, fine. So that means I am going to come up with 2 v prime y1 prime. Okay. So if because I have already assumed that y2 is also a solution of, say, this equation 1. So if you plug in the value of y2 over 1, so then what you are going to get, like, okay, so let me start with this. Let me start with these two. Okay, so for this, if I take v common, so then y1 double prime, this is gone. So then px y2 prime. So from here again, if I take v common, then px y1 prime, and then if I plug in y2 equal to vy1, so if I plug that in here, this is going to give me qx y1. Is it okay with everybody? Fine. Okay. So then I'll be left with what? I'll be left with what? I'll be left with this one and this one. Is it okay? Fine? Isn't it?
Yes, sir.
So I am going to be left with, I mean, y1, and then this is 2 y1 prime plus y1, this. I'll be left with this. Okay, so if I plug this in, I'm going to get this as 0. Is it okay with everybody? Fine. So now, if you look at the expression within the parentheses, you know that since y1 is already a solution of the given equation 1, so that is why this part is going to give you 0. Is it okay? Fine. This part is going to give you 0. So then, if this is 0, then I will be left only with this part. I will be left only with this part. So then, what are you going to get from that part? From here, this part, I can simply write it as v double prime by v prime. This is equal to minus 2 y1 prime by y1. And I missed one thing here. Just a minute. See here, px, it is y2 prime into px. I have missed that px part. Are you getting my point?
Yes, sir.
Yes. So I have missed that px part here. That px part here. Okay. So this is going to be simply minus px. Okay. So now if you integrate it, see this I can what? I can integrate for v prime, isn't it? This I can integrate for v prime. That is going to give me. That is going to give me your ln p prime, and this is minus 2 ln y1 minus px dx, and from here I am going to get your p prime equal to this is going to give me your 1 by y1 square, then e to the power minus px dx, e to the power minus px dx. Is it okay? Fine. And from here, I can get your v equal to simply this square dx. Okay, so simply plugging y2 equal to v into y1, and then you get a fundamental set of solutions. So now I was expecting a question from this step to this step and this step onwards. Could you figure out what was the question that I was expecting? See, integration is perfect. Integration is perfect. What I didn't do there, usually what we do.
Integral constant.
Exactly. See, here, I didn't omit any concept of integration, right? Can you tell me why it is so?
So actually we are finding linearly independent solutions. So
Yes.
From the linearly independent solution, finally we shall get the general solution. So in the general solution, we are putting
we are
constant.
going to adjust the constant there. Okay. Yes. So is everybody getting me? Let me explain what he was saying. Say, I could have easily get a concept of integration here, right? So from there, I would have got a constant of integration here, say k. Now, if I plug in here the value of v, I will have some k into something, isn't it? Right? But when you are going to consider a general solution, the general solution is going to come as say yz, that is going to come as lambda 1 y1 plus lambda 2 lambda 2 y2, right? So these constant of integration I could easily absorb with that constant of integration. Sorry, with that constant here, lambda 2. Is it okay with everybody? So that is why whether you have a constant of integration there or you don't have, it doesn't matter. Is it okay? Fine. So now the thing is that I have assumed that y1 and y2 they form a fundamental set. So that means y1 and y2 are linearly independent, and I have also found out the explicit expression for y2 in terms of y1. So now, can you tell me, what is the guarantee that they are linearly independent? Can you prove the linear independence of these two? So for that, what you have to do, you have to simply prove that the Wronskian is non-zero. Is it okay? You have to prove that the Wronskian of y1 and y2 is non-zero, right? So what are you going to do? You already have this y2 equal to this one. Okay, so then you are going to plug this in, right? In the formula for Wronskian, that is your y1 right? Are you going to do that or not? I don't know why you guys are so silent. How do you prove that the linear dependence and independence?
Sir,
So,
if they are linearly dependent, that means one function is the scalar multiple of another. But here v is a function of x. So it is not a constant.
But what is the guarantee that I mean, like say you may have a function, where the combination of v y1 is going to make it a constant, something like that. Okay, I got your I got your point. So now see, if you have to use Wronskian concept, then what you are going to do? Are you going to do the whole stuff? Let me tell you one thing. Why I am just I mean making all this kind of confusing stuff. I am doing it just because you don't have to worry about anything. You simply use this expression. You simply use this expression, right? And what you do, simply plug this in here. And for y2, for just a minute. For y2 prime, you simply plug in this, and for y2, you simply plug in y1. Okay, so then one term will vanish. I mean, one term will cancel out. From the remaining term, you can easily prove it. Okay, so are you getting my point? You are going to get something like v y1 square or something like that, I guess. V prime y1 square, you are going to get that. And you already have the value of v prime here, isn't it? Fine. So if you get v prime y1 square, you are going to be left only with this term, which you know that being an exponential function is non-zero. Is it okay? Fine?
Yes, sir.
Yes, sir.
Right? My point is that you don't have to go all the way of differentiating these functions once again. That is simply going to be waste of time. I am telling you that simply make use of this expression here and plug that in here, because you have already found out v prime from here. Okay? And eventually, I mean, find the final answer. Fine? Okay. So,
hello,
this
sir.
is about, yeah.
Yeah, sir. Are we? Because we are assuming that y2 is a solution of the form v times y1. So,
Yes.
are we assuming that y1 does not vanish anywhere on the interval? Because if it does, y1 vanish somewhere on that interval? Because if it vanishes, then y2 also vanishes same at that point.
y2 vanishes at that. So even that, I don't need to worry about. See, yeah, I got your point. Probably you are confusing because don't confuse it with the property of Wronskian. That thing I already told you. Okay, we have already discussed the property of Wronskian that throughout the whole interval, Wronskian either vanishes or doesn't vanish at all, right?
Yes.
But
yes,
that
sir.
is not the case with the functions.
Okay.
Okay.
Yes.
That is not the case with the function. The functions may vanish at some point, but still they can be non-zero at some other points in the interval, isn't it?
Sir, I'm actually confused because we are considering y1 to be a solution, known solution, and then we are finding y2 another solution. So that means already we are assuming that.
This is fine. See, okay. See, let me answer to this question. Definitely, I am not going to take your y1 as the trivial solution. Okay.
Yes, sir.
y1 not equal to 0, because if you take y1 equal to 0 throughout the whole interval, like say, I mean, then you know that any set containing the 0 vector is always dependent, linearly dependent.
Yes, sir.
So, right? My point
Yes,
is that, okay, Like say, I am not saying that I am taking y1 to be a non-trivial solution, right? And now your question was y1 may vanish at a point. Okay, let it vanish at a point, but that doesn't necessarily mean that it is going to vanish at all the points in that particular interval. Is it okay? I'll come back to that. Don't worry about it. When I am going to talk about qualitative behavior of solutions of ODEs, then whatever you have said, vanishing of the function at a particular point, that is going to be very, very important. Okay, and probably you are going to get answers to what you have asked me right now over there. Okay, just hold on for a, I mean, half an hour more, and probably you are going to get your answer there. Okay, fine.
Okay, sir.
Okay, so now this has given you an idea. This has given you an idea of using another function, as in order to using a known function in order to determine another unknown solution of the homogeneous differential equation. So now what we are going to do, okay, fine. Okay, let me come to another interesting aspect from this Wronskian. This is very, very important. So I will, yeah, okay, fine. See, let me come back to this same equation because I'm going to be using this over and over. Okay, okay, let me come back to the same equation. Okay, fine. So now, see, I have been emphasizing that I am going to get a fundamental set, right? I have been emphasizing on A, not D. Okay, so that means the fundamental set of solutions is not unique. For example, yeah, you tell me what is the fundamental set here? Yes, it's pretty straightforward.
Sin x and cos x.
Sin x and cos x. Okay, so this is the fundamental set. This is a fundamental set, fine? But you can easily prove that sin x and sin x minus cos x is also a fundamental set. You can easily show that. So that means the fundamental set is not unique. Are you getting the point? Isn't it?
Yes.
Yes, sir.
Right? So once we know a fundamental set, right, we can use a workable combination of the elements in the fundamental set to produce another fundamental set. Isn't it? So that means it is not unique. Okay, fine. So we cannot do anything about it. Now, the question is whether you can do something about uniquely determining the coefficients px and qx in terms of the fundamental sets. You get my point? What I mean by saying is that suppose that you have found out that y1, y2 is a fundamental set of the given fundamental set of solutions of the given differential equation 1, right? So can I uniquely determine the coefficients px and qx in terms of y1 and y2? And the answer is yes. Okay, the answer is yes. So what I'll do, I'll just quickly tell you what you got to do. See, since y1 and y2 are solutions, so solutions of 1. So definitely your y1 double prime plus px, y1 prime plus qx, y1 equal to 0, and then y2 double prime plus px, y2 prime plus qx, y2 equal to 0. Okay, so what you have to do in order to find out px and qx, what you have to do, firstly you eliminate qx, right, For that, what you are going to do, you are going to multiply it by y2 and multiply it by y1, then subtract 1 from 2 or 2 from 1, and then from there you'll be able to find out px. Is it okay? Fine? Yes?
Yes, sir.
Yes,
Yes,
sir.
sir.
Next, in order to find out qx, you are going to simply eliminate px, right? So in that case, you are going to multiply this equation by your y2 prime and this equation by y1 prime, and you are going to get it. Is it okay? Is it okay? So then, you
Okay,
will
sir.
see that you are going to get px as and your qx, this as you are going to get as this. Okay, and division by the log scan is always valid because it has to be non-vanishing in order for y1 and y2 be linearly independent. Is it okay? So now what you can do? Now you can check. Now you can check. Now you can check from these two. I'm not going to work it out. You just verify at home that if you use this as y1, sin x as y1, and cos x as y1 or y2, then whether see here what px is 1, right? px is 1 and qx is 1, and whether you get that or not. Similarly, you can try with some other equations also. Then you will see that these coefficients are uniquely determined by a fundamental set. Is it okay? Fine. So that is the purpose behind this exercise. Okay, fine. So I guess that was an interesting exercise. That was why I was doing that. Okay, and again, like I just want to give you one example that if you know a solution, a known solution, then how to determine the other solution. Just one example quickly. And like say this particular exercise, I think I have put it in my slide, so we don't need to worry about it. And there, all this stuff, so far, whatever I am telling you today, I have taken them from Simon's book. And again, I mean, I may not be able to upload your assignments, I mean, that frequently, but what I suggest to you is that you try to do as many exercises from the Simon's book. I have figured out that Simon's book, I mean, all the relevant exercises, I mean, pertaining to the chapters that I have taught you, chapters or sections that I have taught you, I think they are workable. You can easily work them out. Please do that, even if I don't tell you to do so. Okay, fine. Okay, so this is a second order linear equation, right? And you can easily verify that y equal to x is a solution. Because anyway, y double prime will be 0 here, I'm not worried about it. Y prime is 1, so this is x, minus again y is x minus x is 0. Fine? Okay, so now if I want to find out the other solution, which is which constitutes a linearly independent set with this solution, so then what I'm going to do, I'm simply I'll find v equal to what? V was 1 by y1 squared. So my y1 is x, right? So 1 by x squared, then e to the power, was it minus px dx?
Yes, sir.
Minus px dx. So what is p here? X?
1 by x.
1 by
1 by x. Yes, because you have to reduce it to normal form. Many of you do in exam, like say this kind of silly mistake. So once you reduce to normal form, this is going to be 1 by x and then 1 by x squared. This is equal to 0. Okay, so this is 1 by x dx. So dx. So this is going to be 1 by x squared. So here it is going to be ln x minus ln x, right? It will power minus ln x. So again 1 by x, right? So 1 by x cube. So it is going to be minus 1 by 2x squared, right? Okay, fine. So your y2 is dy1 and y1 equal to x. So this is simply going to be 1 by 2x. Okay. So basically, I mean, say negative half is a constant. So if you have to find the general solution, of this equation, you can simply write it as c1x plus c2 by x. Is it okay? Fine. And that is the thing. See here now you know. See, I could have written it. I could have written it as this c2, right? But what is this? So I can write it as c1x plus c2 prime x, where c2 prime is minus c2 by 2, right? That is the thing I told you. That when you describe the general solution of y equal to lambda 1 y1 plus lambda 2 y2, that constant of integration, it can be absorbed with this constant. Is that concept clear now? Right? Why
Yes.
the constant of integration doesn't matter while trying to find out the other solution through the known solution. Is it okay? Fine. So this is one example. So now I think I can move to the method of variation of parameters. Okay.
Hello, sir.
Yeah, somebody want to ask something?
Yes, sir.
Yes.
Sir, suppose I have an interval I, and in this interval, somewhere the Wronskian is 0, and somewhere the Wronskian is non-zero.
In the interval, the Wronskian is 0.
Somewhere Wronskian is 0, somewhere Wronskian is non-zero.
It cannot be.
So, what can
It cannot be. It cannot be. No way. No way.
So,
see, that is why you shouldn't confuse about the function being non-zero at some point, 0 at some point. The Wronskian is such a special function in such a way that it is either 0 in the whole interval or non-zero in the whole interval. And again, remember, this Wronskian, its existence is not independent, right? Its existence depends upon the fundamental set of solutions. Is it okay? Or so its existence, forget about, Wronskian of some functions being the solution of a differential equation. Obviously, the property of the Wronskian is going to depend on, those functions, right? So if you are going to consider Wronskian of some functions, right? This can be 0. Like if I am thinking about this simply as some function of x, this can be 0. But when you are going to consider these functions, these y1 up to yn coming from the solution of an nth order differential equation, and if they are linearly independent, then see what happens. Then what happens? The Wronskian
non-zero or linearly independent.
It is non-vanishing, right? And if you are taking them, as say simply solutions of an nth order differential equation, we have already proved, right? Whether they are independent or dependent, the Wronskian is always vanishing or non-vanishing.
Yes, sir. This is clear from the Abel's theorem. I just want to know the concept. Suppose I have two functions, and this function, the Wronskian of these two functions vanishes somewhere and non-vanishing at somewhere. So from that, can we conclude that these two function can be solutions of a OD, second order OD?
Okay, fine. I won't be able to tell about them being solutions, but I'll be able to, comment on if the Wronskian is non-vanishing. Then definitely I can comment that there is a possibility that those two functions constitute a fundamental set of solutions.
How?
Okay, there is a possibility, but I simply because it is not guaranteed that any two functions which are linearly independent, they are going to be solutions of some differential equation. No, it is not like that. There is a possibility of it. Is it okay? Fine.
So, sir, finally, what can we conclude about this? Suppose I can give an example. Suppose some function is x and another function is sin x. So, if you work out this the Wronskian, then the Wronskian is 0 at x equals to 0, and Wronskian is non-zero for x non-zero.
Okay, fine. Now again, okay, that is fine. So that means if you maybe I can construct something. Okay, so any interval containing the point 0, any interval containing the point 0, if you consider this as a solution of, some ordinary differential equation, so then it is going to constitute a linearly dependent set of solutions. That's it.
Yes.
I'll be able to,
But this is
like
contradicting each other. Somewhere it is linearly dependent, somewhere it's linearly independent. So from that, what can we conclude that these functions cannot be a solution of a OD or anything else?
No. See, I can probably construct a differential equation. I can construct a differential equation. But again, the way I have constructed the unique Px and Qx, that that came from only the possibility of some linearly independent solutions. So if they are dependent, I am not sure. Whether I will be always able to construct. But I think in that case, if I am able to construct, so then, like say, the comment is going to depend upon whether the point where the Wronskian vanishes, whether by excluding the point, you can make it non-zero or you can make it zero. So the definitive conclusion I cannot make right now. Okay. To answer your question, probably I'll have to probe a little bit more. Right now, I cannot answer it. Okay. Fine. Okay, so let me now come to the method of variation of parameters. You see, you may be thinking that some of the things are being repeated, but I think along with the working out of all these things that you have already studied, some extra information is also coming out which you didn't come across before. So that is why I am doing all this stuff. So anyway, this method of variation of parameters, it is already a part of your syllabus. So that is why I am doing it. Okay. So, and I did the previous part so that the idea behind, the method of variation of parameter, you were a little bit introduced to that. Okay, fine. So, what is method of variation of parameters? Okay, say this pertains to the non-homogeneous linear differential equation. Okay, and for that, let me consider the second order non-homogeneous linear differential equation in normal form, which is R of x. Okay, All right. So let me call this A. Okay. Fine. So you already know that if this is equal to 0, it gives me the homogeneous counterpart, and you know that the solution of this differential equation A, it is of this form: y equal to yc plus yp, where yc is the complementary function and yp is the particular integral. Okay, and you know that this yc, it comes from the homogeneous counterpart. Homogeneous counterpart. Okay, so now what method of variation of parameter does? Like say, if you already know a fundamental set, if you already know a fundamental set of the corresponding homogeneous differential equation, can we construct a particular integral out of that? Okay, fine. So that is the concept behind, or that is the motivation behind the method of variation of parameters. Okay. So for that matter, say suppose your y1 and y2, they constitute a fundamental set of the homogeneous counterpart. Okay. So then what we are going to do, as before, we'll be thinking that yp, that is a linear combination of this y1 and y2, but again, as before that we did earlier, that instead of using some constant, I mean λ1 and λ2, we are going to use some function v1 and v2 of x in order to get the particular. Is it okay? Fine. So now what we are going to do, like again, we are going to plug in this one in the original equation A, and then we are going to do some manipulation. Okay, so let us figure it out what we are going to do. So now, okay, because I will keep something permanent, not really permanent, for some time. Okay, fine. So now, if I differentiate it, the way I am going to write it down, will you please notice that the way I am going to write it down. Okay, I am going to write it down as this v1 y1 prime plus v1 prime y1, okay, plus v2 y2. Okay, so first of all, oh, fine. So I can write it like this. Okay, but and before proceeding further, let me tell you that in order to determine this v1 and v2, right? So we would be needing a system of two equations, right? A system of two equations, like we would be needing something like that. Ax plus b, something like that. We will be needing a system of two equations, right? In order to find out v1 and v2. Okay. So now, what I am trying to do, I am trying to find out those two extra equations. Okay. The first step, I mean, how we are going to find that out? That we will try to find it out by simply plugging in the value of this here. But for that, I am going to do some manipulation. Okay. The very first manipulation, it is going to come from here. So what we are going to do, we are going to assume that this part is 0. We are going to assume that this part is 0. So that means we are going to assume that your this is equal to 0. Okay, fine. So that means like my yp is simply, sorry, yp prime is simply this one. Is it okay with everybody? Fine. So now again, yp double prime, it is what? Again, let me write it like this: v1 y1 double prime plus v1 prime v1 prime, your y1 prime, right? Similarly, v2 y2 double prime plus v2 prime y2 prime. Is it okay? Fine. So now let me plug this in. Let me plug this in here in the original differential equation. Okay. Fine. So if I plug this in there, so as before, let me try to do this. If I plug this in here, so this is going to give me, okay, fine. So let me first take v1 common. So then from here, I am going to get y1 double prime, right? Then plus px from this part, v1 I have taken common, then y1 this, okay? And then since your y is your v1 y1 plus v2 y2, again from this part I am going to get qx y1. So basically what we have done, we have made use of this term, and this term. Okay. So similarly, if I take v2 common as before, I am going to get this. Okay. So that means I have made use of this one and this one and this one. Is it okay with everybody? Is it okay with everybody? Right?
Yes, sir.
So
Yes.
basically, I am left with your v1 prime y1 prime plus v2 prime y2 prime, and since it is a particular integral, since yp is a particular integral for this equation, so what is going to happen? If you substitute the particular integral, you are going to get the non-homogeneous term. Is it okay? Fine. So as you know that y1 and y2, they were nothing but the solution of the corresponding homogeneous equation of A, right? So that is why this is going to give you 0. Similarly, this is also going to give you 0, right? So from there you are going to be left only with this, right? So that means you are going to be left with what? This is equal to Rx. Fine. Okay. So I have already told you that we were seeking some two auxiliary relations, right? Which is going to provide me with the solution for the term v1 and v2. But okay, if you look at the equations, I'm not getting v1 and v2 explicitly, right? But what it is giving me, like say, because y1 and y2 are explicitly known, so as their derivatives, isn't it? Right? So if I know this, so then definitely I can have right? Isn't it? So as I have told you, now I have something like this. Isn't it? From here I can easily find out v1 prime and v2 prime. So let us use Cramer's rule. In order to solve these two equations. Is it okay with everybody? Fine. Okay. I want to keep this here because I would like to tell you something more. Okay, so if I solve this, your v1 prime, simply it is going to be what? y1, y2, y1 prime, y2 prime, right? And here, what you are going to do? Simply replace this column with 0 rx, y2, y2 prime. Is it okay? So similarly, your v2 prime, again, this is the same thing, y1, y2, y1 prime, y2 prime. And again, what we are going to do, we are simply going to replace this column with 0 rx. Is it okay? Fine. So that means this is equal to minus y2 rx. What is this? What is the denominator?
Wronskian.
Yes, Wronskian of y1 and y2. So similarly, this is going to give me y1 rx and Wronskian of y1 and y2. Is it okay? And from here, eventually I can get v1 to be simply integration of this y2 rx Wronskian y1 y2 dx, and your v2 equal to y1 rx Wronskian y1 y2 dx. That's okay. And then you already know y1 and y2, so from there you can get it. Is it okay? Fine. See, here the trick is to find a system of equations, system of two equations for the derivatives of v1 and v2. Okay, I'll come back to that again. Whatever statement I made, that the trick is to get two auxiliary equations for the derivatives of v1 and v2, right? So that is why, if you look back here, what we were doing, we were simply plugging this as 0. And you may be thinking that, okay, that was one way of getting one of the auxiliary equations. But more than that, here I want to retain only this, because obviously it is going to make my calculations simpler. But apart from that, from here, once I try to find out the second order derivative, I am going to get, you may be asking me, why not this as 0? Why not retain this and retain this, but not this one? Because if I plug this and this at 0, what is going to happen? From here, if I want to find out the second order derivative, so then I am going to be left with y1 prime. Whereas, in order for the original differential equation, the homogeneous counterpart of the original differential equation to be satisfied by y1 and y2, I will be needing the second order derivatives of y1 and y2. That is not going to happen. Okay, if I chose it like that. Okay, fine. So this is the thing, and you can easily verify with some. I'll do one exercise. Let me do the exercise, then I'll come back to this part again. What's the time? Okay, I can do. Okay. So this is nothing but method of derivation of parameters, or a second order non-homogeneous situation. Okay. Fine. So I'm trying to solve this equation by the method of variation of parameters. Okay. So can you tell me what is the linearly What is the fundamental set?
e to the power x, x into the power
E to the power x, x e to the power x, right? And simply I will d minus 1 whole square. So there is a repeated root. That is why this x e to the power x. I think it is okay with everybody. So this is your y1, this is your y2, right? And here your rx is simply e to the power x 1 plus x squared, right? So if I want to find out the Wronskian, this is e to the power x, x e to the power x, then again e to the power x here, e to the power x plus x e to the power x, okay? So basically you will be left with e to the power 2x. Is it okay with everybody? Fine. So that is why your v1 that was what? Minus y2. Y2 is this is x e to the power x. Okay? Rx is this one. E to the power x 1 plus x squared. And then divided by the Wronskian. Wronskian is e to the power 2x. Fine. So this is going to give you minus x by. Okay. So this is what? What?
minus half of 101 x square plus
X squared plus 1. Okay. Fine. And then V2, then V2 is y1, that is the same thing. Like I am simply going to get 1 by x squared plus 1 dx, isn't it? V2 only minus x will be missing, isn't it? Is it okay with everybody?
Yes, sir.
Right? So this is, I mean, 10 inverse x. Okay, fine. So that means if you have to find the general solution, what it could be? So if I call this 1, so therefore a general solution of 1 is y equal to c1 e to the power x, c2 x e to the power x plus your v1 y1, right? So v1 is this, so minus half ln 1 plus x. So maybe I will write e to the power x here, and then plus x e to the power x 10 inverse. That's okay. Fine. So now, okay, yeah. Now I'm going to push something for you. So this is about method of variation of parameters. Okay. Fine. Can I erase this? You have probably noted it down, right? Yes?
Yes, sir.
Okay, fine. So now, what I'd like to do, I'd like to extend this concept of method of variation of parameters to higher order equation. Okay, fine, to higher order linear equation. Now, suppose you have something like this. I mean, NF order. Right, PN, it's fine. This is equal to say f of x. Okay, so now let me call this as A. Okay, fine. So what did I tell you? See, it boils down to find out two auxiliary relations in the previous case, right? In terms of V1 prime and V2 prime. Is it okay? So similarly, here what we are going to do, we are going to assume that your y1, y2 up to yn, it constitutes a fundamental set of solutions, right? And then I am going to assume that yp, this is what your v1, y1, v2, y2 to vn, yn. Okay, fine. And from there, I try to develop the methodology. Okay, so now, okay, let me just do the first order derivative. So here, what we'll have to do, we'll have to find derivative up to nth order. Is it okay with everybody? Yes?
Yes, sir. Yes, sir.
Because I would like to substitute in the given differential equation, isn't it? And it is an nth order differential equation, okay? But let me first try to do, I mean, the very first. So obviously, you know that from here, I'm going to get this is one part, and the second part is going to give me maybe let me write it like this. Fine. As before, what we are going to do? We are going to discard this part. Is it okay? Fine.
Yes, sir.
Yes.
We are going to assume that this is equal to 0. So that is going to give me the very first equation for the system of n equations in the unknowns v1 prime, v2 prime, vn prime. Okay, fine. So let me try to write it down systematically here somewhere. Okay, so the first equation I got. Okay, you will understand. This is equal to 0. Fine. So since I have already plugged this in 0, that means my yp prime is this. Is it okay with everybody? Right? So then what will be yp double prime? As before, what I am going to do, I am going to take this as v1 y1 double prime up to vn yn double prime, right? And then again the second part, you just simply concentrate here. You just simply concentrate here. So it is going to give me y1 prime v1 prime up to isn't it? Is it okay with everybody? Just think about taking derivative of this term. So this into derivative of this is the first term, and then derivative of this into this. This is this term. Is it okay?
Yes,
Yes,
sir.
sir.
Yes, sir.
Then again, what we are going to do? We are going to assume that this is 0. Isn't it?
Yes, sir.
You are getting the point? So that means I am getting what? Right? So now your yp double prime simply it has become this. So in this way, if I proceed in this way, if I proceed, then eventually, what I am going to get, your equal to, yes,
0. Sorry, Rx or Fx.
Rx, or in this case, f of x. You can check this. Okay, so in this way, we are going to be left with this, isn't it? Fine, because once you plug in all these values in this equation, right? So then you will be left with only this term, because all the other terms, once you plug that in here, right, that is going to give you 0, and eventually you are going to be left with this. Is it okay? Fine. So then, what is going to happen? I'm just going to show you this slide, so that you have understood the methodology, right?
Yes,
Yes,
sir.
you have understood the methodology. So I'm just going to show you this slide so that I don't have to write it down. Okay. Yeah. So please look at this. Okay. So if you look at this, then these are the equations, right, that I have generated. So as before, if you want to solve it through Cramer's rule, then what you are going to get, you're simply, I have written it as V1 prime. So V1 prime will be simply what? You are going to have the determinant from the Wronskian, right? So the first column of that Wronskian, you are going to simply replace by your this 0, 0, 0, everywhere 0, but the last one is f of x. Is it okay with everybody? Fine?
Yes, sir.
Yes? Okay. Say the first n-1 equations in this system, like this equal to 0 in 4. That is nothing but what we did for the second order equation. Okay. So our assumptions that are made to simplify the resulting equation after yt equal to this is substituted in the given differential equation. Okay. So in this case, Cramer's rule gives your, in my case, it is going to be bk prime. This is going to be wk by w. K goes from 1 to n. So where, of course, w is the Wronskian of those n functions, and wk is the determinant obtained by replacing the kth column of the Wronskian by the column consisting of the right hand side of 10. That is the column consisting of 0, 0 up to fx. Is it okay with everybody? Fine? Yes? So now, I mean, you can just, now you know the procedure for nth order. Right? So basically, I mean, if you understand, I mean, see, I mean, the books, what they do, many of the books, I mean, they don't describe the things clearly. Like, so they will simply just follow a procedure, and eventually we will arrive at some beautiful expressions, and we are excited about that, and okay, we are happy. But as a PhD student, you shouldn't be, I mean, happy as you used to become earlier, right? You used to go for more. Why this is happening? Why that is happening? Okay. So once you know the clue, it is very easy to extend something which you have done for lower order equations to higher order equations as well. Okay, fine. And I had sent you a mail to you guys about studying the extra material stuff. So have you studied it? No? Okay. So if you still haven't studied it, please, I mean, go through that extra material stuff that I had uploaded, how derivatives affect the shape of a graph. Okay, because in my next class, that is tomorrow, I'm going to talk about your quantitative behavior of the solutions of ordinary differential equation. So over there, all those concepts are going to come in handy. Okay. So with that note, I'm going to end today's class. So definitely I'm going to meet you tomorrow at 12.
Sir, I have a question.
Yes. Yeah, tell me.
Sir, where this method